the past questions, I can't really promise you that, but the only thing that I can help with, as usual, having a lot of questions in my slides. Is that okay? I don't keep track when it comes to past questions and other things. And I told you before that.
Okay, say I didn't finish.
Sorry. Finish. Sorry. So, please finish. Sir France. Is it France?
I was like, I would have played that where we have to get understanding of a concept. You have to take your time, take us through there. Because one of these days, we also teach the learners. The pace, we have to slow it down a little bit. For 4 weeks, I think we can finish with.
Okay. Sure. I'll do that, Sir France Quadmana. And Sir Charles, about the answers in the slides, I think that is fine. But I'll not solve all the details. Maybe I can provide just the final answer that you're supposed to get. Is that okay?
Final answer is okay.
Yeah. And Madam Patient, when it comes to past questions and other things, I'll not lie to you. I don't keep track with this. In fact, when we start, I told you it's different people that handle these things. So my coordinator maybe will be at the right person to do that. But I think you can just be asking our seniors. When I say seniors, those who just completed or they finished. Is that okay? It's the same course you are teaching them, so I think they can help with that. Is that okay? I'll not lie to you. Right after teaching over the weekends, over the weekdays, I am very busy because I'm also handling regular students too here. I'm taking like 3 courses, So sometimes the way I've forgotten his name. He was calling to ask for the slides to share to you, but I will see the message. I will say, "Oh, Charlie, I'll send it later. I'll send it," and then I'll forget us. So, pardon me for that. If I'm to keep this track of this one, I'll disappoint you. Thank you very much. So I think we can start. If there is no consent so far.
Okay. Thank you.
Okay. You're welcome. So for the atomic physics, these are the things that we just need to know, which you know already. But the most important thing that I want us to look at right now is, do we have any idea when we mention the word atomic physics, what comes into mind? Atomic physics. But let's hold on. Maybe when we mention something like off the content, when I see something like wache, what comes into mind? Food wache, what comes into mind?
Say, is that when you say wache, what is it?
Yes, when I say wache, what's the first thing that comes into mind?
In fact, wache is food.
Very good. The first thing that comes to mind is food.
Yes.
Then what is the next thing that comes into mind? What kind of food?
Yes, it will be rice.
Rice. We know that we're expecting rice, we're expecting beans. Is that okay? And we're expecting it to be colored one way or the other. So we know that you're talking about wache. Now, when we see atomic physics, what comes into mind? What's the first thing that comes? Atoms. Perfect. Is that okay? So that is what we are coming to look at here. Now, in fact, the birth of atomic physics didn't start today. It started very long time, and the time that our great-great-grandparents were dealing with slavery and magic and superstitions and traditions and other things. The whites were breaking some boundaries. Is that okay? But even before breaking the boundaries, they were also having some phenomena that they were also using before that break of boundaries came. And that time it was the ancient Greeks, which was led by the Aristotles. whatever being the case, let's say right now that we are talking, when I throw something to the sky, a ball or anything, I'm expecting the ball to come back to where I am or to come to Earth. Is that okay? And when something like that happens, what is the first thing that comes into mind that allow the ball to come back? Do we have any idea about that?
Gravity.
Gravity, perfect. Is that okay? That is through an experimental procedure, and we had something called gravity. But the olden times wasn't like that. When I say olden times, I mean the early physics, the Greece time, the Aristotle time. That time, they were presuming that anytime I throw something to the sky and it comes back, it means it is trying to reach something we call the natural place. Is that okay? There was nothing like, okay, gravity. There was nothing like some Newton's law that is explaining these things. And another thing too was the fact that you wake up in the morning, then a sun come, we see a sunrise, we see a sun going down again. Then another morning also comes. In fact, even that time, the Aristotles were saying that even with that thing, the universe is trying to also move to its natural place. Is that okay? So we get things move, we get time go, because they are all trying to reach what? Its natural place. And in fact, all these things that we are talking about, there were no experimental thing to buttress it. It was just a mere presumptions of what is going on. Is that okay? So, okay, I wake up in the morning and evening comes. I'm expecting Aristotle to explain. Aristotle will tell me that because the earth is trying to, or the universe is trying to go to its natural place. Is that okay? So there was no instrument or no anything to buttress what was going on. Now, it was during this period where this man came, Galileo. Is that okay? And the whole thing about Galileo was trying to bring some experimental physics to explain what the Aristotles were also what saying. Okay, so you are saying that when we wake up and I see morning and I see evening, I see morning again, I see evening. They're trying to go to the natural place. What is the experimental ways that we can do to prove for this? So when I trace something up, I'm expecting it to come down. What is the thing that is going on that explains these things? Is that okay? In fact, Galileo did a lot, but didn't finish. Then 100 years down the line, this man came, that is Isaac Newton. And that is where you know the Newton's law. And now you are doing Newtonian physics. Is that okay? So all the laws that you are going to see in terms of how macroscopic, when I say macro, I mean big objects, they move. Is that okay? So he came to explain all these things, how motion is going. Why is it that when a car is moving and I'm inside the car, I jump, I get some force of motion that is going to push me somewhere? He was explaining that. Why is it that when I leave a pen on a table, whatever being the case, I go and come back 100 years, it's still going to be on the table? He explained that. Is that okay? Why is it that if there's something on the table and the force I'm using it to push is not stronger than the exerting force on it, it doesn't move? He explained that. Is that okay? So Newton came to explain this whole thing in terms of what Galileo left and in terms of what the Aristotelians were also presuming that these things were happening. Is that okay? Which is very important. Now, the foundation of this experimental physics actually did a very wonderful work during the 19th. You know, it is that time that we started having rockets go to other planets to go and observe the planetary system. And it was through the laws and the experiments that Newton did. Because we know that if something is moving, you need this amount of force and energy or mass to let it move. Now we understand gravity. We understand gravity of other planets. Then if that is the case, we can build a device, put a rocket in, inject some fuels, let it go up the sky, and it can go to a different place. During these calculations, Is that okay? But even with Isaac Newton's numerous works that he did, there were still some limitations, because everything that Isaac Newton was doing was big, big objects. He's talking about how a car is moving or how a car stops, how a rocket can move, how a rocket stops. He's talking about how you can run. And when you run and something pushes you, the reason why you are falling. He explained all these things in a macroscopic level. Is that okay? And when I say macroscopic, I hope you understand. Macro. Do you understand macro?
Yes, sir.
Perfect. In a
That's
macroscopic,
mm.
that's big, big sizes. Is that okay? But everything that he did was having a limitation because the laws were not able to represent the microscopic level. And when I say micro, you understand micro, right? Do you know micro?
Yes, sir, we do.
Perfect. So micro is MICRO, micro, small, small objects.
Please.
So
Yes.
Newton's law were not able to explain, like the Murphy-Molly law experiment was not able to explain body radiation, was not able to explain photoelectric effects, was not able to explain why we have some spectral lines in an atom, and all these things. That was a very big drawn or boundary when it comes to his laws. Is that okay? So fast forward, this man also came as Albert Einstein, and he also did a very wonderful work. Is that okay? But this is
Yes.
what we are come to explain. A thing that is important for us to explain under atomic physics are these things. Is that okay? So all the things I started talking about is a prelims. I just want you to be familiar with history a little. Now, the atomic physics, this is how the outline is going to be for us. We are going to talk about Prost and Dalton atomic theory. We talk about J.J. Thomson. We talk about Ernest Rutherford. We talk about the drawbacks of both J.J. Thomson and Ernest Rutherford. We come and talk about the hydrogen spectrum. We talk about Bohr. Bohr was actually a student of Rutherford and Chadwick. We talk about them. Then we talk about their shortcomings or their drawbacks. Then we talk about, I think this one I didn't add it to the slides, but if there's a need, I'll add it. The spectrum of ionized helium infinite mass correction. Then we'll jump straight to what you call X-rays. Is that okay? Then we'll talk about their numerous application of X-rays. So this is going to be the outline for atomic physics, which I am hoping to finish within this time. Is it possible?
Yes.
It's
Today.
It's possible. Yes, today.
Okay.
Anyways, atomic physics is more of history. Is that okay? And I'm very sure that most of these things we are very familiar with it. Is that okay? So don't worry, I'll still take my time through this. Please hold on. Summarize one slide. Let me see if I can find that one. Okay, so I'll stop presenting this one, then I'll share another slide. I think I updated the slide, so let me show you the one I updated rather. Please, can you see my slides? Perfect. So let's continue with where I ended. Perfect. So now the question that I have for the class today is, how do we know the structure of the atom to be today? As of right now, December 2025, how is the structure of the atom? Everyone is going to talk. So give me your understanding of how you know the structure of the atom is going to. It's like right now. Who is starting, please?
Sorry.
So I would say atom is the smallest particle
Mm,
of an element that can take part in chemical reaction.
But I want the structure. How do you know the structure to be right now? When you say atom, how is the structure like? Now, right now, if I say I am Rabi, and I can actually describe myself in terms of structure. Say I have a big head, I have a big nose, I have a big eyes, I have a small cheeks, I have a big chin. My body size is this, my waist size is this. Is that
Okay,
okay?
sir, let me come in.
Mhm.
I modeling the structure of the atom. I said the atom consists of what we call protons and neutrons within what we call the nucleus. And around the atom, that is where we have electrons orbiting around the atom.
Okay. Thank you. Any different submission?
Hello.
Yes, I have
Let me
some. I have
try.
to say. Yes. Mm-hmm.
Okay, like what my brother just said, the atom, it have a nucleus. That's one thing. It have a nucleus. And inside the
Mm-hmm.
nucleus, that we have the proton and the neutron. And around is what
Mm-hmm.
we call the shell. It's on the shell that we found the electron that move around the shell. And one thing is that the proton and electron are stuck inside the nucleus, so they don't move. They are stationary.
Okay.
It's only the electron that orbit that move around the shell.
Okay.
And the electron carry the negative charge, while the proton carry the positive charge. It carry the charge of positive. And the
Okay.
neutron doesn't have a charge.
Mm.
Uh,
Okay. That's perfect. Any different submission? How is the structure of the atom like today?
Hello.
Yes, sir, I'm listening.
Please, to add to what my colleagues have said, the nucleus of the atom is actually where the mass of the atom is concentrated, because the protons and the neutrons, they are massive. I mean, they carry some weight. For that matter, they being in the nucleus makes the mass of the atom to be what? To be concentrated in the nucleus. And then greater volume of the atom is also covered with empty space. And then you have the electrons, which are having negligible mass, orbiting around the nucleus of the atom in shells. That's what I want to add to what they have said. Thank you.
Okay, that's perfect. So, thank you. Now, let's go through the birth of this whole atom that we are talking about. As we said, if we talk about something called atom, or we mention the word atom, we know that it's the smallest particle that we will find in the matter, right? Now, we know that matter too has its own different states. Is that okay? Now, if we take the atom, we expect that, as a noun, we expect that there's something inside the atom. that is centralized inside, and that thing we call the nucleus, and it contains the protons and neutrons. Is that okay? And there's something too that is revolving around it, as we said, in its own orbit. Because if it's not in a particular orbit, we can imagine the fact that these electrons will be crashing. Is that okay? And it's like the planetary system. You can imagine the planetary system like this, where we have the sun at the center, and we have all the electrons that is revolving around it as our planet. Earth has a particular orbit that it has to use to what? To repeat. Is that okay? If it doesn't have that, you see that Earth will crash with, let's say, Pluto or Mercury or anything. Is that okay? But it has its own path that it has to take. And that is how we know the structure of the atom to be. If we are to dive more, we can actually talk about their magnetic side and their electric side and their sub-shell state, like the SPDF and other things. Is that okay? And how they even spin and other things. But that is not going to be our work today. But what I am very interested in right now is letting you know that this thing doesn't or didn't come just like that. It started giving birth from a place before we had this. A lot of scientists worked on it before we have this conclusive example. Now, it all started from one man who was an English teacher as at then. His name is John Dalton. And you know, as usual, I told you about the Greek philosophers, the Aristotles. They were all having their presumption when it comes to how matter is supposed to be like. And in fact, they said, yes, we have something we call atoms in a matter, but this time around, and they even gave a name to it, and they say that it's called atom. But one thing is that this atom can never be breaking down into smaller pieces. That is how the Greek said it. So it was down the line 2,000 years later, then this man came, John Dalton came, and who is an English teacher. And he came to disprove this particular presumption that the Greek philosophers said. Is that okay? And as at that time, they were not having equipped instruments to actually perform a good experiment to prove the existence of atom. So interestingly, this John Dalton, English teacher, did his experiment in a macroscopic level. Is that okay? He presumed it in a microscopic level and later gave us his deductions and how he thinks the atom is supposed to be like. Is that okay? But at the end of the day, that thing one read under said that this atom cannot be divided into smaller pieces and cannot be destroyed. And he gave a lot of postulates around it. Is that okay? And this is his 5 principles of how he said the atom is supposed to be like. Is that okay? The first thing that he was saying is that, please, can we hear me?
Yes, sir.
So
Yes,
as you
sir.
go.
Yes, please.
The first thing that thing said is, you know, if we have a matter, in fact, he said that all matters is made up of indivisible and indestructible atoms. Anytime you have something like a matter, that is what we believe to be in. Now, the next thing that he said about how the atom theory is supposed to be like this, that these atoms have the same element. Atoms of the same element are identical in physical and chemical properties. Is that okay? So if we have atom A and atom B, and they belong to the same element, we expect that both their physical and chemical properties to be the same. And the third thing that John Dalton said is, atoms of different elements have different physical and chemical properties. So if atom A and B belongs to different forms of elements, we should be expecting these 2 properties to be also different. The next thing that he said, that atoms of different elements combine to form what? A simple whole ratio. Is okay, which is very important to form a chemical compound. And the last thing that he said is atoms can not be subdivided, created or destroyed, but it's what it recombines or rearranged or combined and separated. So there's no way that you can create an atom. The atom that exists, that is what we are just working around on Earth. So you combine them, we arrange them, we separate them, and that kind of sort. But I have a question for the class. With these 5 postulates, this postulate or principles was in the 1800. Which of them still exists to be correct in 2025? Let's look at it very well. Which of them still exists as 2025?
Sir,
Yes, sir.
I can see atoms of different elements combined in simple whole number ratios to form chemical compounds. I see this one exists. Then
And the last one.
Atoms of different elements have different physical and chemical properties.
So hold on. The first one that you are saying is correct is what?
You said
okay, this is number 1. This is number 2. This is number 3. This is number 4.
I have opted for 3 and 4.
Okay, so 3 and 4. Can you justify this for me, please?
Okay. Atoms of different elements have different physical and chemical properties. When you take like hydrogen is an element on its own, and when we take sodium too is an element on its own. Both of them, they behave differently. Hydrogen behaves different from sodium. And atoms of different elements combine with simple whole number ratios too. If you want to have a compound, we take 2 different elements and these as a compound. Sodium plus chlorine will give us sodium chloride.
Okay. You have
Yes.
a little background in chemistry, yeah?
Yes.
Still?
Sir, you said what?
Are you doing chemistry still?
No, I'm offering physics.
Any different submission, please? With these 5 postulates, which of them stands to be correct now as of 2025? Or they are all not correct.
They are all correct.
They are all correct. Okay. Can you justify it for me? So this is the question. So which of these principles remain true today? State with reasons. Are we thinking about it or we are confused? Yes, Hassan.
Thank you. I think my first colleague has said it all. Like the very two principle, the fact that atoms combine in simple whole numbers to form compound is still correct, because if you are combining atoms to form a compound, for example, if it is carbon and oxygen, you cannot have C1.5 or 3.7. You can't have something like that. It's always, they always come in what? In discrete whole numbers. Then about the fact that atoms of different elements behave and chemical properties, I think he was able to explain that when we take something like hydrogen and sodium, they have different, properties. For example, at normal temperature. So that's a different. Will undergo, which hydrogen will not undergo. So I think that is all that he said. I think I perfectly agree with him.
That is fine. So that is the 3 and the 4. Now let's go through what I have here. So the first postulate that thing said is, if we have an atom, there's no way you can divide it again or into any different forms again. But in as much as we can't break it into 2, we have subatomic particles of an atom. Is that okay? Atom doesn't stand as a whole as the smallest. We have other sub ones under them. Is that okay? So it means that the first postulate that thing said, this one, as a noun that we are talking, it is wrong. Is that okay?
Yeah.
Then he mentioned the fact that if atoms are of the same element, it means they should have some identical properties in terms of physical and chemical. But as a noun that we are also talking, we have something we call what? Isotopes. We can have the same atomic number, but this time around, we can have different mass numbers. Is that okay?
Yeah.
Because of the different neutrons that it has in the nucleus. So if that is the case, it means that we may have some variation one way, the other somewhere. Is that okay? Even if an element like chlorine, they may have some different mass numbers, about 35 and 37, which at the end of the day, we may have some different physical properties that may differ, which is very important. So it means that as I know, in 2025, this still doesn't stand. If the second one doesn't stand, it means maybe the third one can stand. Is that okay? Which is a very perfect answering for the second one I just explained. Now I have atoms. If they have different elements, of course, I'm expecting that the property is supposed to be different, whatever being the case. Is that okay? At least we have some properties somewhere that is going to differ. And in fact, it's their properties that isolate them in terms of their group numbers in the periodic table and in terms of their, I think I'm getting some feedback. Is it from my end? Okay. So we may be getting some atoms what they are different, and of course we expect their properties to be different too. Now let me tell you the next one that's hello, can you hear me?
Yes, sir, we can hear you.
Sorry, I went off a bit. Now let's go on to the fourth one, which Sir and Alhassan also commented on. And it's very true. Anytime we have things, we can combine them to form, of course, a chemical compound. That is why we have sodium, we have chlorine. At the end, we have something called the sodium chloride. We have hydrogen, 2 molecules, we have oxygen, we have H2 and other things. Is that okay? So that thing John Dartin said is perfectly right. as a now that we are talking, it still stands. Is that okay? Then the last one, atom cannot be subdivided, created, they are rather combined and rearranged. You know, this last one has a lot of arguments in different perspectives. Someone can say it still stands. Someone can also bring in the fact that as a now, there's something we call nuclear reaction, where we have something we call nuclear fission and nuclear fusion. Is that okay? If we are able to go through this process as and now that we are talking, it means that the creation and the destroying of these things, they are possible. Or subdividing them, they are possible, which is very important. Is that okay? So if that is the case, it means that it could be that the last point that that thing also gave, as at this year 2025 December, it still stands to be wrong. Is that okay? If we are explaining we are bringing nuclear reaction to explain this. In fact, it could be that next year, next 2 years, a decade to come, a century to come, these two may not even stand. Is that okay? It could be that one of you will come in as a scientist to come and disprove one of these things. Is that okay? So as a now that we are talking, we have these two to be correct. Only these two. That is, atoms of different elements have different physical and chemical properties. And the combination of these atoms to form what? A compound. So please, let's keep it in mind. Now, I want us to look at the next experiment that was done during the same period. You know, as at that time, there were, I think I told you about Benjamin Franklin when we were doing electrostatics in general physics. Then I mentioned the fact that Benjamin Franklin helped us to discover the positive and the negative. Is that okay? It was something that was in existence already. And you know, there was a lot of experiment that was going on there. And through him, we have something like charges repel and unlike charges attract. So there was a man who took advantage of this experiment. And even that time too, Faraday were also using a chamber to do an experiment already. So J.J. Thomson brought in the idea that why don't we use the same chamber to do an experiment using Faraday's discharge tube, and we called this one a cathode ray discharge tube. Is that okay? And this discharge tube is working like a chamber where we can get it as a vacuum. Is that okay? So we have this whole chamber here. Is that okay? Then we try and pop out a lot or as much as the gases that we have here out. Then when you do that, we're expecting to get low pressure and what? Very high voltage inside there. Then because of what is going on in here, it means that if we have a charge plate here, we have a charge plate here, even if they are not in contact, and this charge plate here releases some small charges, we get the high chances of this one going to this end. Is that okay? Because there is no gas to interact its movement. Please, are we understanding it a little? Is that okay? So now we have inside here a very high voltage. Now we've placed, you know, as usual, we're expecting the terminals to have a contact before there will be a charge flow. But we've created a vacuum. Is that okay? And we expect that this cathode is releasing some charges already. But as at that time, they didn't know that. It's now that we know, and I'm explaining that. So it releases some charges, but because there is no air interaction in here, we pump out all the gases. Then, of course, these charges that you get here will transfer to this anode here. Is that okay? Which is very important. So this was what J.J. Thomson used. Is that okay? Now let's look at something here. Please, do we understand the setup now? Should I go on? Okay. Now, this is what he did. So, you see the cathode that we have here. Let me write something. It will be very difficult for you to use your eyes to see these charges move from the cathode to the anode. So what J.J. Thomson did as at that time is to create some holes here. Is that okay? We have the plate here, but he has just created some holes here. And behind the anode, he has placed something we call the zinc sulfide. And I don't know if you remember etikopo. I'm not sure we still use this, but remember the etikopo, the television etikopo.
Yeah, we do.
Perfect. I think when I was teaching my regular students here, I was explaining the etikopo principle and they were not understanding. They are kids, 18, 17, 19, so they didn't know the etikopo. Now they are using LEDs. So the etikopo, when you break the glass, you can see some fumes or some powder coming out. I don't know if you've experienced any of these things before.
Yeah.
Perfect. That is the zinc sulfide. And what this one is doing is that anytime there are charges and they hit on that particular zinc sulfide, it glows. Is that okay? It lets it be excited. In the form of being excited, it glows. So that's what the zinc sulfide is doing. Is that okay? Some people call it the fluorescence powder, but it's called zinc sulfide. And if we are doing physical optics, I'll also show you more of these things in future. Now, the most important thing that I want us to know here is that is what J.J. Thomson used behind here. And the main reason of using that is at least we will get some charges being released here. Is that okay? And at the end of the day, we expect it to move to the anode. But because we can't use our eyes to see our naked eyes to see these charges, some of them get to the anode, leak from the anode, and gets to the zinc sulfide. And of course, we expect it to glow. So when it glows, we say, okay. He did this experiment and say, okay. So it means that we have some particles in there that can be our smallest particle that is being released from the cathode to the what? To the anode. So after observing this, he called this thing that was released from the cathode side as what? Cathode ray particles, which is very important. So this explanation that I've did is for your just an understanding. So you've seen that I've written the zinc sulfide here again. But when he did this one, he summarized this thing into 3 ways. He summarized that anytime he does this one, the cathode ray starts from the what? The cathode side and move to the what? To the anode side. It doesn't move opposite it. And the next thing that he said is, this thing that he did, he can't use his eyes to what? To see it, naked eye to see it. So he needed what? Any fluorescence or phosphorescence material to do that. And that is the zinc sulfide I mentioned. So that when the charges hit on it, it glows. Is that okay? And all these things that he did, he said that the rays traveled in a straight line. But if traveling in a straight line, he added that even with this experiment, there was an absence in what? Electrical and what? Magnetic field. This is the 3 discoveries that he summarized his experiment to base on. Then with this, later on, he said that the cathode rays that he saw consist of a negatively charged particles, and it is called the what? The electrons. And this is the birth of what we call the electrons we know today. Is that okay? Now, J.J. Thomson, through this experiment, said that these cathode rays are negatively charged, and they are located what? In all what? Atoms. Is that okay? And he added something up. But after the experiment, he has defined that the electrons has a charge of negative. But we didn't know the value of this charge. Is it negative 20, negative 20.5, negative 2 times 10 to the power 28? We don't know that. And even with this one, what is the mass of this atom or electrons in the atom that you are talking about? How heavy is it? Is it massless? J.J. Thomson didn't talk about that. Is that okay? So it became another conspiracy to investigate him after this discovery. Is that okay? So he did another thing, a little modification of the one that I showed you earlier. The same cathode ray discharge tube. But this time around, his aim was to find the charge or the mass. Is that okay? Now, you remember the one I showed you, it just ended here. Is that okay? Where we're having the cathode, we're having the anode, then we have some holes straight in. So it goes straight, then it hits the zinc sulfide, it glows, then we see what is going on there. Now he has added a little thing in here. And what he has added is, he has added two fields, both magnetic and electric field. Please, are we following? I'm confused.
Yes, sir.
So fast forward. What J.J. Thomson did is, now he was varying a lot of things here. He was varying magnetic field, the strength of it in terms of magnitude. He was varying electric field in terms of magnitude again. He was varying the amount of charges that or power or voltage that he was applying at the cathode part. All these things is to be able to find the charge and the mass ratio of this electron he has discovered. And these are some of the things that he concluded or he observed when he was doing this experiment. Now, the first thing that he's saying is these cathode rays bend towards the positive plate. So they must be what? Negatively what? Charged. Another thing that he said is that when I say bend, this means it moves from the cathode to the anode. I think the English here is not correct. It's okay. Bend, it means it has deviated. Then the next thing that he was saying is the deviation. So this is where the deviation comes. There was a lot of deviation going on. And you can see from the diagram that I'm expecting the cathode to go straight to B, point B. Is that okay? But due to the magnitude of the electric and the magnetic part, it can either go to A or go to what? To C. And this deviation was very dependent on a lot of things. And the first thing that he said is that it was strongly dependent on the charge particle if it's higher, one. And also if it has a low mass. And it makes sense. Something that it has a low mass, you can easily pull it. It's like a child running past you and a grown-up running past you. The child has a low mass, so you can easily touch the child or pull the child or push the child anywhere. Not like the grown-up person. Exactly. And the last thing that you also added in terms of the deviation is the fact that we're having a what? A field strength that is being higher. When you say field strength, we are talking about the magnetic or the electric. So basically, it means that this electric and the magnetic field were causing the deviation, which is very important. And the other thing that we can see is that lighter particles, of course, deviate more, and heavier particles what? Deflect less. Then, if looking at all these things, how the deviation was happening, the amount of charged particles that was supplied, the mass of the charged particle that was supplied, and all of these things, and the magnetic field that is being applied there, then it means that J.J. Thomson can conclude on a value for us. But interestingly, he was still not able to find for the charge and the mass. But this time around, he was able to find the what? Charge to mass ratio. Is that okay? With all these experiments that he did. Now, the charge to mass ratio that he was able to find for us was 1.75 times 10 to the power 11. And of course, coulombs per watt, our per kg. Now, this is very important when you look at it in a different perspective. If we have a value like this as a mass, charge to mass, it's very big. I don't know if you are seeing the value I'm talking about. It's 10 to the power 11. It's very, very big.
Please, your line is breaking.
Hello.
I don't know if it's on side.
Hello, can you hear me now or still?
No, it's okay.
Okay. So I am saying that if the value of this charge to mass ratio that J.J. Thomson had comparatively is relatively big, is that okay? And the value of this huge is very dependent on a lot of things because you are talking about charge here and because you are talking about mass. It means that it could be that this electron has a very large charge or it has a very small tiny mass, which as at that time too, they still didn't know. Is that okay? So if we are considering the value as J.J. Thomson is given, this could be the two possibilities if we do further experiments. It could be that the charge of these electrons we are talking about is very, very large, or it could be that the mass that this electron has is relatively small, like very, very, very small. Is that okay? Now let's go on. So fast forward. This experiment also came, and this is called the oil drop experiment. Have we heard of this experiment before? Anyway,
No.
okay, that is fine. So as at that time, they still have a value for charge to mass, but individually finding for the value for the charge, finding the value for the mass, we all don't know. Is that okay? So now that is where Millikan came in. Is that okay? So Millikan came in with this setup to come and define or find any of the values that J.J. Thomson ended at. So he was trying to see if he can find the value of the charge or find the value of the mass. Is that okay? And this experiment is quite straightforward. What Millikan did was that he had this chamber and he called this whole chamber as oil drop experiment. And he has a first chamber up here and a second chamber down here. And these plates are electrically charged plates. Is that okay? It has a microscope here, and it has a ray here that is submitting some radiation to it. And again, you can't see this thing with your naked eye, so we have to excite it before you can observe it with your view through a microscope. Now, the most important thing that we have to know is this atomizer sitting here. I don't know if you know an atomizer. Most of the times, even when you use a spray, you see when you spray, it comes with small droplets. Is that okay? That one too is an atomizer. I think even the women, they have this perfume, small perfumes they keep in the bag. You call it atomizer. I don't know. Madam Patient, will you confirm this for me? Am I speaking the truth here? Is Madam Patient online? Okay, maybe she's not. But do we have any have we heard of any atomizer before anyways? Okay. So when you use the perfume, you see how the drop comes out. So it comes as small, so they call it atomizer. But this atomizer is relatively small as compared to the perfumes, or like very, very small, which you can't see with your naked eyes. And we have a first plate here, and we have a hole at the center here. So at least when we spray the atomizer or the oil spray comes out, we will get a few drops that is able to pass through that small hole. Then we excite it and we view with our eyes. Now, all the variations that was going on here under Millikan was to be alternating these fields, looking at the time is starting here to get to this last end and other parameters. Is that okay? And through this experiment, Millikan was able to define the actual value of a charge for us. Is that okay? Which is negative 1.602 times 10 to the power negative 19, which I know you know this value already. Is that okay? The charge of an electron. So you managed to find the charge of an electron. And luckily for us, J.J. Thomson has defined the charge to mass value for us. So if that is the case, we can use these two values to find for the mass of the electron. And it's very simple. You just divide the charge by the charge to mass, then we'll just get our mass of the electron. Have I managed to confuse you, or you are following? Am I online?
We are following you, please.
Okay. Perfect. Now let's go to the next thing. Now, right after J.J. Thomson's experiment, he concluded on how he presumed the atom supposed to be like. And here we call it what? The model of the atom. And we are talking about the getting to the 19s. And this is what J.J. Thomson said. He said that, in fact, when you take an atom, hold on. When you take an atom, this is how the atom is supposed to look like. And the atom here is just a full round thing like this, which is full of positive, and it has negative stacked or uniformly around it or distributed in the atom. And you can imagine this one as we have the watermelon. Is that okay? Where all the watermelon, the red part is the positive. And you see we have some seeds in it, which is ununiform in it. Is that okay? Sorry, it's uniformly, not on uniformly. In it, is that okay? Which is going to be our negative. Is that okay? So we have the seed in the watermelon as the what? As the negative. And we have all the red part as the what? As the positive. So these ones, the seed in it as the negative, the food that we are going to eat is the what? Is the negative, which is very important. That is how his model of the atom through his experiment said that this is how the atom is supposed to look like. Now fast forward. Ernest Rutherford came in, and Ernest Rutherford was having these two students, and they tried to see, or let's say, try to experiment on what J.J. Thomson did. So if we are saying that if we have an atom, it's supposed to be something like this, which the whole part of the atom is positive, and we have some negative that is distributed in it like this. We want to perform an experiment to prove what you are saying the atom is supposed to look like for us. But let me ask the class a question. If I have something like this, and I have another strong positive charge coming in here to come and bombard with the material, what do you think will happen? Are we online, or we are thinking about it, or we are confused? Which of them?
Your network is breaking. So the last thing you said, I didn't get it.
I'm saying that if we are presuming this to be our atom, that is what J.J. Thomson has told us. And I have another molecule here, or say a particle here, but this time the particle coming in here is positive. Is that okay? Strongly positive. And I want to bombard with an atom that J.J. Thomson presumed to be like. Is that okay? And he's saying that all the atom is positive, but it has negative distributed in it. And I'm asking the class, if I bombard this positive with the atom of J.J. Thomson, what do you think will happen?
Please, I'm Solomon. I think initially it was neutrally charged because the number of positive charge and the number of negative charge are equal, making it neutral. So with the bombardment of that extra positive charge will make the atom become a cation or positively charged.
The best way to explain this one is light poles repelling each other, unlike poles attracting each other. Is that okay? That is the best way we can use to explain the phenomena here. I'm just giving a tip. Any answer for me, please?
Yes, sir.
Mhm.
Yes, sir. So, this is Hayford speaking.
Okay.
When you look at Thomson's model of the atom, it's like it's made up of a sea of protons, positive charges, with a few electrons inside. So when you are bombarding it with another atom of positive charges, it means when the positive charge from that atom goes into that of Thomson's model of the atom, there will be a collision of charges which will cause a deflection. That means the proton is likely to deflect back to the atom or deflect into different directions. And if it has to meet the electrons in that atom, then there will be attraction. That's what I think.
Okay, perfect. Any different submission? The way we are not giving submission, it means we are not understanding what is going on here.
No. The question I didn't get a question clear actually.
Okay.
In
So
particular.
I'm saying that, you know, J.J. Thomson said that the whole atom is positive. The whole atom is positive. And we have negative charge that is distributed in it. Is that okay? Uniformly. Now, if that is what we have as how we propose the atom to be like from J.J. Thomson perspective, I am saying that if the atom is sitting here and I am bringing in a different particle that is purely positive, I want to bombard it with that atom. What do you think will happen?
Okay.
So I think that will be repulsion.
It
Report.
means that there will be, because already, according to J.J. Thomson, if he's saying that the whole atom is positive and it contains negative electrons distributed inside, so that means that the concentration here is based on the positive. And if we are bombarded with another more positive, it will create the whole atom to. So it will be more it will be more positive, or the positive will now go to the positive that is coming. In that case, the negative now becomes smaller or very smaller.
So
Okay.
I also think it will cause it to scatter.
It will cause it to do what?
Scatter.
Sir,
Yeah, hello,
sir.
Francis. Yes, sir.
Yeah, I think since the alpha particles are positively charged and then the inner part of the way too is also positive, it means that the negative charges, the alpha particles will pass through it. Most of them will pass through it very easily, with only a few of them deflecting.
Okay, let's bring this scenario on board. Maybe the class will understand. You know how watermelon looks like. This is
Yeah.
exactly what J.J. Thomson is saying the atom is
Yes.
like. All the red part inside that you eat is positive. All the red part, everything inside is positive. And you see how the seeds are distributed inside. Is that okay? That is going to be our negative. Now, let's imagine the fact that the red part that we eat, we have another red part that is sitting here, the one that we eat, which is positive. And both the red part that we eat, it doesn't meet because positive, it will repel. Is that okay? Only positive and negative that will attract. Now we have another red part that is coming to enter that watermelon. What is going to happen? And remember, red part doesn't meet. It will repel. If it's negative, they will of course attract. That is what I'm asking the class.
Okay, so in that case, the mass of the positive will increase the more. Because already, if the mass, if the whole atom is positive, that means it overweight the C, which is the negative inside. And when we are bombarded with another positive, it will cause the mass of the positive more increase and reduce the negative, which is the C, more. And in that case, it's like if the mass is higher, it will cause the distance to explode. It will cause the watermelon to explode.
Okay.
Because the mass of the red part become more. Because when we are adding more, it is the mass of the red part, which is the positive, is higher. We are bombarded with another more. We are adding another more of the red part, which is the bombardment of the positive. So it increase the mass of it and reduce the mass of the. It make the seed inside very small. In that case, if the mass is of the proton is higher, it will cause the watermelon to break or to scatter, like somebody used the word inside. Thank you.
Okay, that is fine. So what we are discussing right now is exactly what Ernest Rutherford did. Is that okay? So he was having something we call alpha particles, and you know this alpha particle is purely positive, and it has a very strong mass. Is that okay? And we have a lead plate. In fact, lead plate is something that can block the alpha particles. And we've created a slit inside so that only some fraction of it in particular magnet of direction will pass through. So this is how we manage to figure it out. Then we have our matter. Now, J.J. Thomson is saying this is how atom supposed to look like. And a normal matter like a gold foil also supposed to have a model like what J.J. Thomson is presuming is supposed to look like. Is that okay? Now, if that is the case, we expect that what J.J. Thomson is telling us that we have a positive here, We have the whole positive and a negative here. Ideally, if I have another positive entering this kind of a matter, I'm expecting most of them to deflect back. Positive, a lot of positive inside there. The only situation that will allow this one to go through is if it has an encounter with a negative. What are the chances of getting an encounter with a negative? Is that okay? So that is how you all presumed that the experiment should go. That is how J.J. Rutherford presumed that if I put my gold foil here and you bombard it with these alpha particles, I'm expecting that at least most of them should deflect back. Most of them, of the alpha particles, should deflect back. But one interesting thing happened. Almost all of them passed through the alpha particle. Sorry, passed through the gold foil. Almost all of them passed through the gold foil, which is very interesting. So it means that how J.J. Thomson model was proposed to us, there's a question mark somewhere. Okay, so if this is supposed to contain all positive, now at the end of the day, another positive is going to pass through all of them. There's a big question mark somewhere. Is that okay? Which means that how you are proposing that the atom is looking like, it's not like that. Is that okay? Which is very important. So I've shown you how the configuration of this experiment is. We have the alpha particles, we have our lead plate, and we have the photographic plate. Is that okay? That is just going to let us see what is going on. We can't see with our naked eye, as I mentioned earlier. So it hits on it, you get some reflection and you know what is going on. Now, I've explained all this. This is what was going on there. Most of them. So this is what he observed. The first thing that he observed is that most of the alpha particle passed through the gold foil undeflected. The second thing is a very small fraction of these alpha particles was deflected. Then with even the deflection, it's not a deflection of bouncing back, it's a deflection of changing the angle. So if we have our atom to be this, and it was bombarded this way, if it passes through, instead of it to go through, it deflects and go this way. Is that okay? This is the deflection we are talking about. And even with this deflection, very small amount deflected. And now the next thing that Rutherford observed is that very few of these alpha particles bounced back. When I say bounce back, went back to where it's from. And here, the amount that is actually bounced back is relatively negligible. We are talking about 1 out of 20,000. And even with that one, its deflection or bouncing back was nearly around 180 degrees. Is that okay? So it means that there's a very big question mark to what J.J. was telling us. Now let's show you something. So at the end, this is what Rutherford explained what he observed. The first thing that he was saying that these alpha particles are very heavy, relatively, and electrons cannot sufficiently deflect them, which also makes sense. So any deflection should be in the form of any mass or positive charge inside the atom. But in a situation where we have most of these alpha particles passing through our atom, it means that the atom is what? It's mostly empty space. And it's not like a solid sphere that what J.J. Thomson proposed. Is that okay? So if you are saying all the atom here is positive charge, and most of them is able to pass through, it means that it could be that yes, we have a positive in, but it is not in all of the atom. Is that okay? It could be that positive is there somewhere. That is why it didn't deflect back or bounce back, but pass through. Please, are we understanding? Perfect. Now let's look at another thing.
Yes.
Under the same explanation. So now I've explained this one to you. Now, when you're talking about the large angle deflection, It could be that this alpha particle came close to a concentrated what? Positive charge. Then it means that, yes, we have a positive charge inside, but not as proposed as J.J. Thomson. But they are sitting inside somewhere, and the chances of you meeting it will let you deflect. Is that okay? And another thing is that it's not all of the region that will be having a what? This positive charge. We could have still seen a bounce back of most of them. So this is how Ernest Rutherford concluded his observation. He said that the atom we are talking about, and J.J. Thomson is saying all the atom is a positive charge. It's not like that. If we have most of the particle pass through, it means that the atom has its most of the space empty. It could be that we have a hollow thing, a big thing here, and it's hollow. That is why the positive charge was able to just pass through. But the fact that we had a deflection somewhere means there's some charges inside it. But these charges it's not big. They just concentrated at only some small portion of the what? Of the atom, which we don't know whether it's sitting left or right, but we know that there's something in that is very, very small. And this is what's causing what? The deflection. Because when you bring the alpha particle coming in, if it meets this one, then it will deflect by, sideways. Maybe if it meets it at this end, then it will deflect this way. Is that okay? So this was the second conclusion. And at the end, he concluded that, yes, we have something we call the positive in, which is the what? The nucleus. As at that time, he hasn't found the nucleus, but I just wrote nucleus here. And he said that from his experiments and his measurements, he said that the atom has a radius of what? 10 to the power negative 10, which is Armstrong. But the nucleus that we have inside, that is the part that the positive is, that is even way smaller than the atom itself. So here we are talking about the radius of this whole atom. Is that okay? Now, that is the 10 to the power negative 10. Now the next one is the nucleus, the radius of this nucleus, the thing that is sitting inside here, the radius of it. That is 10 to the power what? Negative what? 5. So we are talking about 100 times smaller than the actual radius of the what? Of the atom. This is relatively very small. And he ended that since we have our almost all the mass in the nucleus, then it means that we have a proton-like mass existence inside that nucleus. So from the observations and the conclusions, Rutherford made a conclusion on how he thinks this thing is, and he created his own model of the atom, which is an update of what J.J. Thomson did. And the first thing that he said is that the nucleus contains most of the positive charge and mass. And this time around, we are talking about small dense core, and that is where the protons lives. And he even proposed that how he saw the atom to be is relatively the same as how the planetary system is, where we have the nucleus in the middle as the sun, and we have something we call the electrons that is sitting around the nucleus. Is that okay? And one thing too that he added is that there's some force of electrostatic attraction that is keeping the electron moving around the nucleus. And I've taught you electrostatics, so you have to understand this. So now fast forward in the 19th still, that is where all these things have surfaced and the nucleus and the protons came in place. In fact, as at that time, they didn't actually have exact word as protons for it. Is that okay? But they knew that there was a positive charge inside there. The name proton later came in when they did an experiment where this time around they bombarded a new nitrogen atom with the alpha particles again. And that is where they had that particular word proton for it. Is that okay? We knew it was just positive charge, positive charge. Is that okay? With everything that Rutherford did, there was still some drawbacks because electrostatic force is not strong enough to keep electron moving in its orbit forever. Won't there be any form of electric attraction because there's a positive sitting in the middle and there's a negative moving around? And all these things Rutherford didn't explain to us. Because even apart from that, if you are saying electrostatic force is keeping it, which is fine. If the electron too is moving around the orbit, with time, it will lose energy. Because, when it's moving around the electron, the nucleus, as it's moving, it constantly dissipates or emits electromagnetic radiation. So it will move for some time, then maybe drop to the nucleus, which with time, our atom will collapse. So here, Rutherford didn't explain that. The next thing he didn't explain something called the energy levels. So we have a nucleus here. We have electrons around it. Yeah, say lucky.
Yeah, please. With the electron loses energy, is it going to speed? Is it going to speed the speeding? Is it going to inside the nucleus? Is it going outside the nucleus?
It will go inside the nucleus.
Okay.
When in terms of energy levels, in general, in chemistry and in physics, it's supposed to move outside the nucleus. But in terms of electrostatic force, if it has lost its energy and there's here, it will go inside the nucleus because of the force of attraction. Is that okay? Because this time around, there is no force that is keeping it to move around. Is that okay? And since we have a positive sitting in the middle, it's just going to attract it to itself. But in terms of energy levels, which I'm coming to explain right now, if something loses energy, it moves away from the nucleus. I don't know if you understanding, but I'll explain that to you with this one. So he couldn't explain the energy levels in terms of how these things sit at the orbit. Who gets the chance to sit closer to the nucleus? Who gets the chance to sit far away from the nucleus? What is going to be the energy that I need before I can sit in shell 1, shell 2, shell 3, or shell 4? Is that okay? So all these things Rutherford didn't explain. Selaki, do you want to say something?
Yes, your line will break off when you explain the energy level, but it just off on.
Okay.
I don't know if it's only me that experiences.
So I was saying that for the energy levels too, Rutherford couldn't explain because the question is which electrons gets to sit on the first energy level? What does it need before it sits there? Do I need more energy before I sit there or less energy before I sit there? Is that okay? So these are the things that Ernest ended his conversation. He didn't explain that. So it was a very drawback when it comes to his postulates. So fast forward, his students also came in. So they were trying to explain the fact that why we need another form of energy or particle existence in there. And they prove for this actually. Let me show you. Okay. They prove for this actually. So what Chadwick did is that in the 1932, he did another experiment which he bombarded beryllium with what alpha particles, and that is where they had something we call the neutrons. But this time around, this neutron has a mass which is slightly heavier than the what? The protons, which we'll talk about it later if there's a need. And we have something again that Rutherford also brought in place, that if we have an atom, it must always remain what? Electrically neutral, meaning that something must also what? Exist. And that is where we have something we call the what? The neutron in there. So when you take the nucleus, we have the neutron in, and we have the what? The proton in there. Is that okay? And outside it, we have the electrons that is revolving around it. Now, Bohr also came, another Rutherford student, so Neil Bohr, and he did a very wonderful work because Neil Bohr came in to explain a lot of drawbacks from Rutherford's experiment. And that thing is there, even in scientists. So right now that I'm here, I have a supervisor, and the work that my supervisor is doing or my professor is doing is the same research that I am also doing. So if he's not around, or when I grow into the research, I will one way or the other take up to what he was doing. And that is how scientific research has been for the past decades or centuries. Is that okay? So one day I'll also get a postgraduate student. He will also come and do my research. If I'm not there, he will continue with the research that we ended, unless the individual wants to divert. Is that okay? Apart from that, student takes up their professor's research and grow into it. Is that okay? So that was what was also going on there. So Rutherford has done his part. His students were taking up the depths or the drawbacks that he created and try to correct them. Is that okay? And Rutherford all issues was coming from the fact that he is trying to solve the problems of particularly the energy levels. So he brought his model of the atom, and he was having four important principles, which we'll be talking about a lot. Then the first thing that he said is that electrons occupy only certain orbits around the nucleus. Those orbits are stable and are called what? Stationary orbits. The second one that he also talked about was their energy levels. And he said that each orbit has an energy level associated with it. You don't just come in and come and sit at the first shell or second shell or third shell. Your energy will let us know where you have to sit. If you have low energy, we have a particular shell you have to sit. If you have a high energy, you have a particular shell that you have to sit, which is very important. Now, he added up that the orbit nearest to the nucleus has energy level what? E1. And the next one is what? E2. So if this is my nucleus, the first orbit that I'm talking about, this one, this is going to be my E1. And the second orbit like this is going to be my E2. And that order. So the another orbit that comes is going to be my what? E3. That is what he is talking about. Now, let's look at this one, which is very important. Energy is absorbed when the electron jumps from a lower orbit to a high orbit. And energy is what? Emitted from a higher orbit to a low orbit. Now, anytime we have an electron that is sitting here at the top here at E3, the energy that it has is greater than that of the E1. The same way, the energy that electron sitting at E2 has is greater than the one that is E1. Is that okay? The further E7 should have more energy than E6, E5, E4, A3, E2, and E1. Is that okay? Please, are we understanding?
Yes, sir.
Perfect. That was the whole argument. Is that okay? And Bob was saying that if you are at E3, is that okay? And let's say you want to come to E1. After getting to E1 straight away, you emit some form of what? Energy. Is that okay? Because your energy is stronger than going to E1. So you take some of your energy, let you go to E1, where your energy matches there. The same way, if you are at E1 and you are going to E3, your energy doesn't matches E3. So you have to absorb a form of energy, either photon or heat, sorry, in the form of a photon or heat. Then after getting that amount of energy, we move you to what? E3. Is that okay? So that is how the emission and the absorption comes in here. And then the last thing that he added is that, we can calculate for the frequencies of this, the energy of this, and we have a formula to do that. And I'm sure I have exposed you to this formula already, or maybe if it's our first time, this is frequency equals what? Change in energy divided by E. Where our change in energy here is a E2 minus what? E1 divided by what? H. So here we have our high energy, our low energy relatively, and H is a Planck's constant. Please, are we okay? Should I continue? Very good. Now, there's one important thing too that we have to know, and here is what we call the radius. Is that okay? For each shell, we can actually calculate the radius and the energy that each of them has. Is that okay? And it is very simple. We have a formula as Rn equals what? N2 multiplying our A. And the A here is a constant. Is that okay? That is 52.9 picowatt meters. And the N here is a principal quantum number. When I say principal quantum number, we are talking about the levels of the stationary state. So the first one here, closer to the nucleus, is a principal quantum number 1, principal quantum number 2, principal quantum number 3, principal quantum number 4. Exactly, in that way. So anytime you want to calculate for the radius for principal quantum number 1, we will just write our 1 here squared, multiplying our A. That is what? 52.9. Sorry about my handwriting. Picometer. Is that okay? This is how we are going to find out our first principal quantum number is radius. If you want to find the principal quantum number for 2, the radius for the 2, so 2 squared multiplying the E, that is the constant, that is 52.9 picometers. Is that okay? Which is very important. So that is how you find the radius of it. And we can also find the energy. Now, the energy that we are talking about here is the energy that each of these principal quantum number holds. Is that okay? So we can find the energy, and it's very simple. We have this one as our Rydberg's constant, the RH. And again, the N here represents the principal quantum number. Is that okay? Do you want to go for a break and come and continue?
Yes, sir.
Okay, perfect. So how many minutes are we going for a break?
I think 10 is normal.
10,
Okay.
10 is okay.
Okay, so maybe let's go then come back. When it's 2:05, then I'll start. Exactly 2:05. Okay, so let's go for a break for till we meet at 2:05. Yeah, hello.
Hello, sir.
Yeah, are we all in? Can we continue?
Yes, please.
The number is not encouraging. If you have a platform, can you put it on it so that we start right now?
Okay.
Yeah, hello, can we continue?
Yes,
Okay,
sir.
perfect. So we will finish very soon. I think we have about 4 slides. Then we'll go to the extras. Now we've discussed the fact that if we have a quantum number and we have the constant of A naught, we can find the radius of each quantum number or each stationary state. Now, the next thing that I was trying to elaborate on was the fact that we can also find for the individual energy. So say we have a stationary state of say 1 of a quantum number, we can find the energy of that. We can find the energy for the 2, we can find the energy for the 3. Is that okay? And the formula is very straightforward. We have the RH, which represents the Rydberg's constant. Is that okay? And this is the value in joules. That is 2.18 times the power negative 18. And we have our N representing the quantum number. Is that okay? This is for finding the energy for the individual stationary states. We can also find the energy, the change in energy, if we have an electron move from one stationary state to another stationary state, which Bohr explained that. Now you know that anytime you have an electron at a higher stationary state and it wants to go to a lower stationary state, is it going to absorb or is it going to emit? Hello.
Hello, sir.
Yeah, is it going to absorb or is it going to emit? We have an electron at a higher stationary state. Let's say it's E7, a stationary state or quantum principal quantum number of 7, and it's going to, let's say, 5. Is it going to emit some of its energy or absorb some of its energy?
It will emit.
It will emit some of the energy. Is that okay? Because it's going to a lower stationary state. Perfect. Now, the formula I'm showing you here again is for finding the energy for the individual stationary states. Is that okay? I'll show you another one where we can find the change of this energy too. But let's keep in mind that anytime you want to find for the energy for the individual stationary state, as I've mentioned, We are just going to use a straightforward formula as I've shown. Is that okay? Where we have the negative RH. The RH is a constant, which of course it will be given to you. And the n is the principal quantum number. N is squared. Is that okay? So we can find for that of 1, we can find that of 2, we can find that of 3, we can find that of 4. Any stationary state we can find for it. So I've done one example for the first principal quantum number, where we have E1 to be equals to the constant value there as 2.18 times 10⁻⁸ into brackets. Is it showing very well? Yeah, I think I have it down.
No, please, it's not showing.
It's not. Okay, but what I have here is the value of the RH here, and in place the n, we have 1 here. Is that okay? So this time around, please hold on. Sorry, where we have the n to be our principal quantum number. Is that okay? So we just replace the RH with the number that we have here, the value of that we have here, and we replace the n with the 1. Is that okay? And you know that at the end you're supposed to get a negative of this 2.18 times 10⁸, because we have 1 squared here divided by the 1 here is still going to give us 1. Is that okay? And at the end we get this value. So this is the energy for the first stationary state. Please, are we getting it? Perfect. Now let me show you something. Now we've explained the fact that these electrons can move with among the individual stationary states, say higher to lower, lower to higher, and that's such as also. Now, if I have a change in energy, I'm expecting an initial one that it were before, and the new one that it has moved to. It could be that it moved to a lower one, it moved to a higher one. In principle, it's going to emit or absorb energy. That is there. Is that okay? Now we are interested in that change in energy in question. And you know that anytime you're finding the change in energy, of course, you are finding the final and the initial. Now, from the individual energy calculation, we know this formula. Is that okay? So if I am interested in finding, for say, the final, I can just come and substitute this formula and replace with the final. And if I do that, I'm supposed to get, let me write this thing here. For the final, I can get RH divided by NF, which is going to represent the final. Is that okay? Negated. Do we understand before I go on? So,
Sir, please go back again.
energy for the final. Okay, so I am saying that now we are talking about change in energy, not the energy of the individual choices. So I am defining the change in energy. And change in energy, we are talking about change. So you have initial and final, right? So now I'm interested in only the final. Now, if I want the formula for the final, we already have formula for the individual stationary state. So we are just going to change this one to represent our final. Is that okay? And it's the same thing, but this time around, we are just going to add F to the down here to represent the final quantum, sorry, principal quantum number. Is that okay? So if I have something like this, hold on, let me clean this and write it again. Erase. So if I have this to represent the final, I can just restructure this one, get negative RH here, divided by my n squared. But this time around, I have n squared as the final. Do you agree to this? Perfect. Do you agree to this, apart from Frank?
Yes, please.
Perfect. Now, this is going to be the final. So I'm just going to move this here to replace the energy final, which is what I have here. I don't know if you can see. The same thing, negative RH divided by the N with F. Is that okay? Now I'll bring my negative here because it's changing energy. I'm talking about final and I'm talking about initial. Now, in terms of the initial, it's still going to be the same thing, but I'll just replace the F here with the I. Is that okay? So instead of having F, now you can see that I have I down here. So this whole term here, from where I have underlined here, the first term is representing the final energy. The second term is representing the what? Initial energy. Do you agree to this?
Yes, sir.
Perfect. Now, if that is the case, I have a negative here, I have a negative here, of course, I get a positive. And because I have RH as common term in between the two things here, I can bring the RH outside. Is that okay? So that at the end of the day, I'll get the RH into brackets, the 1 over what? N squared I. Here, positive because of the negative that I was having. So this time around, it's not going to be 1 over NF minus 1 over NI. It's 1 over NI squared minus 1 over NF squared. So this whole thing that I have here represents my change in energy. Is that okay? So if an electron moves from a stationary state to a different stationary state, I can actually also find that particular energy that is doing that transition. Do you agree to this? Now I already have a value for the RH. So of course I can represent or leave the equation like this, or maybe like this in joules, and it's still fine. Can I move to the next slide? Now we can also represent it in different forms because there's another formula that relates frequency and energy. I showed you earlier from nearby. And you know that anytime we have change in energy, we can multiply our frequency and the H, that's the Planck's constant, to represent change in energy. If I am interested in finding only frequency, it's still possible. I just have to make the frequency the subject, then I'll get the change in energy divided by what? H. And we've already derived a formula for the change in energy. Is that okay? Now, when we derived, we had change in energy to be equals to my RH, that is the constant, then 1 over what? Ni squared minus 1 over Nf squared. This is what we have for the change in energy. Now I'm bringing in I because I am interested in finding frequency. So if that is the case, you know, Planck's constant is just dividing this whole formula. Is that okay? This is representing my change in energy. So I can bring the H here. That's the Planck's constant. So anytime, another formula, anytime I am interested in finding the frequency of that particular transition between two stationary states, it means you can just use this formula to also do that. Do you agree to this?
Your network is going off and on.
Come again.
I say your network is going off and on.
Is it for my end? Is it the same for everyone? Or it's only like his end?
Everyone.
Everyone, sir.
Everyone. Ah, interesting. Then maybe it's my end. Do you want me to go offline and come back again?
But sir, it's stable now.
It's stable now. Okay.
Yeah.
But anytime it happens, you can tell me, then I will go offline and come back again. Is that okay? So the whole argument is we are trying to see how you can also find different quantities apart from the energy. Now I have shown you how to find the change in energy. I've shown you how to find for the individual energy for the stationary state. And right now, I've shown you how to find for the frequency. Apart from that, too, we can also find something we call the wave number. And you know, wave number is just the inverse of wavelength. Is that okay? So we can also find that. It's just a manipulation and change in equations, which I have done down here. Is that okay? So it's very simple. As far as we know the energy formula, we can just be twisting all these things around. So in future, if you are given a question and it's not about changing energy and it's a different quantity you are looking for, you should be able to do that. Is that okay? The only thing that we need is which state was the electron in and where is it now and what are we looking for? Is that okay? The rest, they are all constants. So when you look at the one that I have here, I have wave number to be equal to frequency divided by C, which now we've already found for frequency earlier. What we just did here, we can substitute and just divide it by C. And at the end of the day, I'll get my, please hold on. Okay, but please, do we understand what I'm trying to enlighten you on? Are you understanding a little?
Yes, sir.
Perfect.
But I have a question.
Please do ask.
Please, what's the meaning of the C?
The C, speed of light.
Okay, okay.
The value is even written here. You see? I don't know. Can you see? Perfect.
I've seen it, sir.
So I'm trying to conclude here. So even with Niels Bohr model and everything, there was also some limitation to what he also did. You know, the fact that he was able to solve some problems with NS Rutherford doesn't make his model purely right in 2025. So anytime his model and his calculation was used, it was very limited in terms of only the first stationary state. And we are talking about only the hydrogens, we can use helium if it's charged. Is that okay? He was not able to look at it in different perspectives. And again, his model and theory was not able to explain some things like the Zeeman effect and the Stark effect. Those who will be doing atomic and modern physics may understand this thing later on. Is that okay? So all these things were part of his limitation. But as of now, atomic physics has actually transitioned into a very wide spectrum. Even in physics department here, I think they do quantum physics. If you are doing postgraduate, you do something like quantum statistics. Is that okay? Which you'll be looking at something like the Schrödinger equation and diving more into Niels models and other things. Is that okay? So this part is just to enlighten you when it comes to how the atomic physics is and the depth of it and how it has transitioned to this end right now. Any questions so far? Before I move to the next thing, maybe in an hour time, maybe we can finish. Any questions so far? Okay, so if there's no question, let's try this work for me. So let's match this. Column A has some discoveries. Column B has some scientists. Match them according to their discoveries. And question 2 is talking about finding the frequency. If we have a photon that is transitioning from principal quantum number 5 to principal quantum number 2. Can we try our hands on this right now? Hello.
Yes, we'll try.
Okay, I hear. I'm waiting. 5 minutes.
Okay.
Hello, please, how is it going? Hello.
Hello, sir. We are still on it.
Oh,
Please, sir, the RH value, no, is it 1.097 times 10 exponent?
no, it's 2 point something. Let me show you.
Okay.
Here's it. So 2.18
Okay, sir.
times is equal to -8. Please, are we finishing? Or we are still on it?
Yeah, almost done.
Almost done. Okay.
Hello, sir.
Yes, sir. You have something for me.
Yes, sir.
Yes, sir.
I had the frequency, or maybe I start from the first question.
No, so hold on, Sir Frank. I want about three of us done before we discuss. Apart from
Okay.
Sir Frank, who is done again, Abek? Okay, Sir Lucky 2 is done. I want the last person. Yes, Samuel, you're also done.
Yes, sir.
Perfect. So let's deal with the first one, then maybe we'll go to the second one. Can someone help me answer them?
Yes, sir.
Okay, so who is doing that? Sir Frank. Okay, perfect.
This is my matching. The discovery of electrons and the plumb padding model that matches to J.J. Thomson. Arrangement of electrons to Niels Bohr. Then atoms as smallest building blocks of matter. Ancient Greece and Dalton. Discovery of nucleus to Rutherford, and then discovery of radiation. That's Marie and Curie.
Okay. Can you come again, Sir Frank? Sorry.
Okay. So the discovery of electrons and the plumb padding model. That's to J.J. Thomson.
Okay.
Then arrangement of electrons, Niels Bohr. Atoms as the smallest building block of matter, Ancient Greeks and Dalton. Discovery of the nucleus, Rutherford.
Okay.
Then discovery of radiation, Marie and Curie.
Okay, that's perfect. Okay. This Maria and Curie, they were husband and wife, but I think unfortunately the wife died of the same radiation. So we've not done that, but I just added it up here. Is that okay? So that is fine. Let's go on to the next second question. Finding the frequency and the wavelength. So apart from Sir Frank, who can help us go through? Sincerely, I don't have the answer for this, but just tell me the procedure that you use, and let's see if we are all on the same path. Who is going to help us with
Sir,
this?
the question 2 or?
Yes, please, the question 2.
Is it the answers?
I want the procedure, how you did it. Are you done with the frequency? Are you done with the frequency?
Yes, the frequency I had 6.88 times 10 raised the power 14 hertz.
So, Sir Lucky, can you guide me through how you managed to get that?
Sir, I didn't use the this thing you what do you call it? I use different formula. So the frequency I use the formula changing.
Okay, I'm listening. I'm listening.
I use the frequency because you change of E over H, which is the Planck, the H stand for the Planck constant. That's the format I use. So with that regard, the change of E will be the E5 minus E2. And the E5 will give us I use negative 0.54 times the E volt. So I just negative 5.54 minus which is the 2. E2 will give us negative 3.39. All into bracket, all multiplied by the E. You know the EV is constant. The constant is 1.6 times 10 raised to the power negative 19. So if I multiply,
hold on. I'm understanding what we are doing, what you are doing, but you know, from the formulas that I have provided so far, we've not solved anything in electron volt. like using the E volt, like the EV that you're talking about. All the answers and the procedures have been, in fact, it's two ways. It's either you solve it through electron volt or you use joules. Is that okay? And let me go back. When you see what we have here, the formulas we have here, everything here is in joules. Is that okay? So there may be some small variation if you are using electron volts and you are using joules to do it. I don't know if you are getting me.
Okay, sir.
So I would prefer we use the joules to solve this, I beg. So we already have a formula for finding the frequency. That is what I've shown here. I want us to use this one. At the end, this is the formula that we are using. So it's just this value that we have multiplying everything that we have in the bracket here. You've been given the initial principal quantum number and the final quantum number. So it's just a matter of substitution and getting the answer in here for finding for the frequency. Please, are you following?
Yes, sir.
Yes, let's try it and give me an answer right now, I beg.
Sir.
Hello, sir.
Yes. Do you have answer?
The frequency I had 6.91 times 10 to the power 14 hertz.
Is it the same as? Are we all getting the same as what Franz just said?
Yes, sir.
Yes.
So you see how straightforward this thing is. That is why I was trying to take my time to break down how you are going to use the formulas. Is that okay? So that we don't complicate things. So you are given to find energy. You go straight forward, use the formula to find the energy. You are given to find, say, frequency. You do the same. If you are given to find, you are asked to find the wavelength to the same thing. So now that we have the frequency, we are all on the same path. Can we find for the wavelength for me?
Okay.
But remember, the formula that we have here is not wavelength. It's for what?
Frequency.
No, look at down here. The top here is frequency, but look at down here. Down
Wave
here.
number.
Wave number, perfect. Is that okay? So
Yes,
let's be careful how we solve this. It's two ways. It's either you find a wave number, when you finish, you find the inverse, or you find the inverse right now and use it to solve. So if you want to use this formula, after finding it, you have to find the inverse of the formula. Is that okay? Because I told you wave number and wavelength is inversely proportional. Are we getting it?
Yes, sir.
Very good. Another way too is we know that energy is equal to frequency multiplying Planck's constant, right? We can actually also find, now we have frequency. We can find energy here. Is that okay? We can find energy here. So if you find energy, It means that the formula, the answer that you had for the frequency, multiplying the Planck's constant, which is going to give you the energy.
Energy.
We are understanding that?
Yes.
And if I have energy and wavelength, sorry, I have energy and frequency, I should be able to find wavelength. It's very possible.
Please, say, what was the answer? Please, the one who mentioned the frequency, what was your answer, please?
6.91 times 10 to the power 14 hertz.
Okay. I had 6.901 times 10. I think that is almost the same.
Yes. To the power.
To the power 14.
Yeah, it's okay.
But was your answer negative or positive?
Positive.
Okay.
There's a relationship that combines the frequency and energy and wavelength. The question is asking you to find wavelength. There's a which also combines the speed of light. Do you know any formula like that?
Yes, sir.
Yes, sir. Yes, sir.
Can you tell me?
Wavelength equals speed of light on frequency.
Wavelength equals what?
Speed of light on frequency.
So it means that if I have frequency, I can find for wavelength. Is that okay?
Yes.
Yes.
So after getting our frequency, you can choose not to go through all this Wahala issue. If I have speed of light, I should be able to find the what? Wavelength.
Sir.
I'm here, sir.
Wavelength is 4.341 times 10 to the power -7 meters.
Okay. Can you come again with that?
4.341 times 10 to the power -7 meters.
Okay. Are we all getting the same thing?
Yes, sir.
Then I think we are done. Very simple. Is that okay?
Okay, sir.
So, sir, please, it means that we multiply, we divide the speed of light over the
frequency.
The frequency.
That is all.
Okay.
That is all.
That is one. Yeah. I can use the energy bank.
So this question is quite straightforward. Is that okay?
Just use your formula.
Very good. Now let's look at something we call the electromagnetic spectrum. And if you remember, when we were dealing with waves, I mentioned this, general physics. Then, in fact, when you're talking about waves in terms of their propagation, we have two types of waves. That is what and what. Can someone help me here?
Please, can you repeat what you said?
If we are talking about waves, we have two types in terms of their propagation. What and what do we have?
Transverse and longitudinal and transverse.
Perfect. But in terms of the medium that they travel to, we have two types. What and what?
Mechanical and
electromagnetic. No, mechanical and electromagnetic.
Electromagnetic, yes.
The propagation is between longitudinal and transverse.
Yeah.
But in terms of their propagation, that is in terms of their propagation. But in terms of the medium in which they travel, we have mechanical and electromagnetic. Now, we said that the mechanical, it needs a medium before it can what? Travel. It can be a solid medium, it can be a liquid medium, it can be a gas. When someone is standing beside me, when I talk and a person hears, it's because there is a medium that is moving that energy. Is that okay? And I even made a relevant example that If we are outside space where there is no gas, and I talk, you may not hear. Is that okay? You just see my mouth moving up and down. So when they go there, they have to be using radio waves and signals to also what communicate. Is that okay? Now, one important thing under the medium movement in terms of not having any medium is the electromagnetic. And I told you the last time that that is why the sun is able to reach the earth. Is that okay? Outside space, there's no gas, but still the sun is able to travel to us. It means that electromagnetic doesn't need any particular form of medium to travel. Whatever being the case, it is fine to travel. Medium or no medium, to travel through. Is that okay? That is what we are coming to discuss. And the electromagnetic waves, we have 7 types of them here. We have the radio waves, we have the microwaves, we have the infrared, we have the visible, we have the ultraviolet, we have the X-rays, and we have the what? Gamma rays. Are we good?
Yes.
Perfect. Now, I showed you one formula as E equals what?
Frequency times Planck's constant.
Very good, HF. And anytime I have a situation like this, if energy here increases, what happens to the frequency?
Frequency increases.
Frequency increases, perfect. Now, there's another relation that you mentioned, formula that you mentioned to me. You said F supposed to be equal to what? No, I think you mentioned lambda. Okay, it's still going to be the same. C over what?
F.
Over lambda.
Over lambda. If this formula that I have, if I substitute it in the first equation, it means I'm going to get E to be equal to what? H multiplying what? C on what?
C
on lambda. Do you all agree to this? Now, if that is the case, anytime energy increases here, what happens to wavelength?
It decreases.
It decreases, goes down. It's inversely proportional. Is that okay? Which is very important. Because of their inverse proportionality here, is going to affect what I'm coming to discuss right now. Now we have something we call the electromagnetic spectrum. The electromagnetic spectrum relates all the radiation in terms of their energy, in terms of their frequency, and in terms of wavelength. Is that okay? So we want to relate the 7 radiations that we have and bring these physical parameters to explain them. In terms of these 7, how is their energy variation is, how is their wavelength variation is, how is their frequency variation is. It's not the same, it varies. Please, are we okay? The most important thing I want us to know is when you have you have electromagnetic radiation like this, spectrum like this, you see how it has been arranged. This is how it's arranged forever. Is that okay? We start from the radio waves, we go to the microwaves, we go to the infrared, we go to the visible, we go to the ultraviolet, we go to the X-ray, then we go to the gamma ray. These are the 7 that we have come to talk about. Now, with these things that we have, let's look at something. In terms of their energy, let's go this way. You see the direction that I've drawn?
Yes, please.
Their energy is increasing. Is that okay? All of them, the one that has the least energy is radio waves. The one that has the highest energy is the gamma rays. Is that okay? But let's look at frequency.
Please, your network is breaking. In fact.
Oh.
It's not breaking.
They may be from a side, please.
So Lucky, please check your connection.
Okay, sir.
Is that okay? So in terms of energy, their energy is what? It's increasing. But one question that I want to ask the class is, in terms of frequency, what is going to happen in the same direction of movement?
Frequency will increase.
Perfect. Frequency to what will increase? Because frequency and energy, they are directly what? Proportional. Anything that happens to energy, we expect the same thing to happen to frequency. Right? So when you look at the chart here, it means that radio waves has the least energy and the least frequency. Gamma rays has the highest energy and the highest frequency. And it's even true when it comes to the chart I have down here. Look at the frequency. This is the highest. There is a power 20. The least, there is a power what? 4 for the radio. Now, let's look at in terms of wavelength. The same direction. Energy is increasing. Frequency is increasing. What do you think will happen to wavelength?
Will decrease.
Wavelength will decrease because it's inversely what? Proportional. And you know, this thing that we are talking about, when we are mentioning wavelength, most of the times we don't say wavelength is increasing, is decreasing. We say shorter and longer wavelength. Is that okay? So where wavelength is decreasing, we say it has a shorter wavelength. Where wavelength is increasing, we say it has a longer wavelength. Is that okay? So let's use that terminologies. So you can see that at this end here, I should have the lowest wavelength. Is that okay? So it means I have a shorter wavelength. So you can see the wave movement up here. You see it's very short, the distance between them. Here I have to have the highest wavelength. It means the longest wavelength. So you can see the variation and the distances between the crest and the trough. It has a longer wavelength. Is that okay? But hold on. Didn't we do this in general physics? We did something like this.
No.
We didn't.
We did crest and trough, but we didn't do this one.
Okay. Please, are we appreciating it a bit? A little.
Yes, sir. Yes. Sir.
Thank you.
So, come again about the longest and the lowest wavelength, avec.
Okay, that's fine, Sir Lucky. So I am saying that, you know, in terms of the direction that I have drawn here, energy is increasing, frequency is increasing because they are directly proportional. But when it comes to wavelength, it's inversely proportional. It means where energy increases, wavelength is going to decrease. And where energy decreases, wavelength is going to increase. But in terms of the direction I've drawn here, energy is increasing. So I'm expecting wavelength to decrease. And I mentioned that in terms of wavelength particularly, we don't say increase and decrease. Most of the times, what we say is we have a shorter wavelength and a longer wavelength. Are you okay, Aleto?
Yes, sir.
Very good. Now let's go on. Now, these things has a lot of radiation in them, 7. We are supposed to take the individual radiations and discuss. So that is what I want to do right now. So let's hold on to these ones. I'll come back to all these ones. How I don't have this. Okay. Sorry. Let me share a different slide. I don't have what I want to explain here. Hold on. But even before we go on, there was one question that I wanted the class to solve. Sorry, let me take the class back a little. Please use 5 minutes to go through this for me. It's not all of them that we've done, but the ones you know, fill them for me. Please, I read down.
Hello, sir.
Yes, please, I read down.
Yeah, Einstein and Niels Bohr.
Okay, so kindly hold on a bit here.
Okay.
I'm looking for this slide to share. I've messed the slides up, so okay. Okay.
Mommy, into what Jared?
Okay, sir, Frank, please give me the answers. I think I've shared it now.
Hello, sir. Hello.
Yes, sir.
Yeah, I have Einstein and Niels Bohr. Okay. So for Einstein, he explained the photoelectric effect, which explains that light is not just seen as waves, but also as particles. And then for Niels Bohr, he developed the Bohr model of the atom, introducing quantized electron orbits.
Okay. So we have from the list that we have here, we are done with, we've done Bohr, we've done, I would say we've done Heisenberg a little, we've done Schrödinger equation, we've done Millikan, we've done James Chadwick, we've done the Democritus, we've done Galileo Galilei. The only thing maybe we've not done here exactly is the Maxwell Planck's, then Louis de Broglie here. The rest we've done, one way or the other. Can you confirm it for me? Am I speaking the truth? Or I'm adding up?
So it's like you're adding up. Some of them you're adding up.
Okay, some of them, that is fine. So one way or the other, we've been using the Planck's constant, right? But we've not exactly done it, so that is fine. But initially, so I'll start with this one. Initially, I explained what Albert Einstein came to do in terms of finding the energy of a particle that is at a microscopic level. We did the ball, and that is what Sir Frank was trying to help us with. Louis de Broglie we've not done it, so this is asterisked. Heisenberg. When I was ending the slides, I told you that now we have quantum mechanics, and we have something like the Heisenberg and the Schrödinger equation that is helping us now. So one way or the other, I've enlightened you small with a line for the two of them. Have we done this or if not? Milika?
We have done it.
You've done it. What about James Chadwick? You've done it. What about Democritus?
I think you've done it.
We've done it, yes. Initially, I told you about the Aristotles, and they brought about the name of the atom before John Dalton came into place. What about Galileo Galilei?
Yeah, we've done that one.
That one too. So it means only two here that you've not done. But anyways, I managed to answer all of these ones for you. Okay. So later on, maybe I'll send it to you, then you take it up. And I don't know if it's already in the slides I shared. I have a lot of slides when it comes to atomic physics. So maybe check the one that I've sent if it's this. I want us to go to something before I come back. So the explanation of the wave that I was talking about, all these things I've explained, so I'll not go back. I want to go straight to the electromagnetic spectrum. Here, I've explained this one too. Now, the most important thing is taking the individual waves and explaining it to you. You know, when it comes to radio waves, that are the things that allow us to have a conversation. Is that okay? We call on phone. When you have a normal radio. In fact, the normal name radio came from name radio waves. Radio actually is a radiation. Is that okay? And it's even in the name of say a radii. So even when you are using a Bluetooth, you are still using a radio radiation. It's okay, and the radio waves. The broadcasting. That is why you start listening to radio. Then maybe you pass Kotokraba, or Kotokraba is close. Is in Cape Coast here. Let's say you pass Namransa. Then later on, you are not getting the signal for Cape Coast FM. Do you know the reason? Can someone help me here?
So can you hammer on the question?
So I'm saying that I am in Cape Coast. I'm listening to radio, like Cape Coast FM. And Cape Coast, I think they have one they call the Asase radio. Right after passing Cape Coast, say Namransa. Namransa is a stretch going to Accra. Is that okay? Then I'm not getting the signal of Asase FM again, or Cape Coast FM again. Why? What is going on? What do you think is going on?
I suggest the wavelength there becomes longer, hence shorter frequency where you cannot, get the signals.
Come again, sir.
I'm saying that
Mm.
you will not hear you not get the radio to hear because, but then the wavelength has become short or shorter wavelength, hence longer frequency.
Okay.
That is why
I think the
signals.
opposite rather.
So
It means that the frequency of the radio.
Okay. So in terms of radio stations, they build antennas. Maybe let me start explaining this one in this way. We are able to talk because of radio waves on phone. So MTN will come to a vicinity and they will build a very big tower there. Is that okay? Very, very big tower. They will come to another. In fact, this tower that they built, it have a distance that it covers. Is that okay? If it's only, let's say, a campus town like Amamuma or Ayinsu or UCC campus, that is the only distance it covers. But because the tower needs to have a conversation with another person outside UCC campus, they build another tower. But this time around, they synchronize this tower with this. So if someone is here, the person wants to make a call. The person calls. You start calling, it signals the nearest tower to you. This tower signals the next tower that you are calling the person to. Then this tower comes to where you are calling. And that is how the conversation goes on. That is why when you go to a particular remote places, you will not get signal to talk because MTN has not extended their tower to that end. Is that okay? And these are all radio waves. Radio waves is not just an open place anywhere. You create it at where you want it to be. And it's the same as the FM that we're listening. Asasi Radio has their tower. It's at Cape Coast. And that is where their tower is effective. You drive past that particular radar. That is all. You will not get it. That same frequency number that you were using for, let's say, Cape Coast FM, will get another different radio station that is registered in that domain. Are we understanding a little?
Yes, sir. Yeah.
Is that okay? So it is very important.
Yes, sir. Yes. Yes, sir. Please, sir, can you explain it in terms of frequency?
In terms of frequency, yes. So it's the same frequency that we are dealing with. It's waves. Anything we are talking about.
Okay.
It's the same frequency. That's why I related wavelength to you in terms of frequency with terms of energy. They are all related. Is that okay? So if I say waves, I'm relating it with wavelength, I'm relating it with the frequency, I'm relating it to energy. Is that okay? But most of the times, our radio, they deals with frequency. Is that okay? AM and FM. Is that okay? So we get it in hertz. But we can actually also get it in wavelength, say in nanometers or meters. We can actually also get it in energy. Please, are we getting it? And it's the same as the phone that we used to make a call. And there's supposed to be some tower somewhere. Unless the radio station has synchronized with different towers outside their domain, or the outside domain is using some online to broadcast. Apart from that, it stays in that domain, and that is all. You will not get anything again. You travel. So last year, November, I went to Togo for a workshop. Right after entering their border, that is all. MTN doesn't work again. You have to get their network provider to get it. But we went to one waterfall at the northern part of Togo. When you stand at one end of the waterfall, you get MTN, interestingly. And they told me a little distance from the waterfall, there's a mountain that divides Ghana and Togo at that end. So our border is around that end. Then it makes sense that there may be a radio antenna there that is able to give me that signal as I'm standing there. I don't know if you understand what I'm trying to say. Is that okay? The whole conversation is there's supposed to be an antenna conversation somewhere before these things work. So you go outside the country, that is all. You and MTN don't have any issue again. Unless MTN has a deal with the other network providers there, you go, you use it, and they have their ways of charging. Again, last, I think 3 years or so, we went to Abidjan. You can use MTN at Abidjan, but the cost is different. They have their own MTN, and we have Ghana MTN. It's like Nigeria. Nigeria too have their own MTN, and Ghana has their MTN. But because of the charges issues and other things, when you go there and you are making a call, I can actually make a call when I'm at Abidjan. But if Ghana here, they are charging 1 minute to say 50 pesos. When I'm at Abidjan, they will charge 1 minute like 5 cedis. Is that okay? Because there's a synchronized network there. Maybe they have a different network provider there, and MTN has collaborated with them or something. Is that okay? So they've synchronized their antennas together to communicate. Is that okay? So at the end, you make a call, but the charges go high. You are here, you can call someone at the UK. It's possible. But we are traveling between antennas, the different countries. So at the end of the day, your cost is going to go very high. They will charge very high. And even with this one, they move from this antenna issue to another procedure on it, which I will discuss with you later. But do we understand and appreciate what I'm trying to say here? Perfect.
Yes, please.
So now that is radio waves. And in fact, radio waves is very, very less harmful. That is the least energy. Is that okay? There's no way someone will tell me when I sleep with phone, it will kill me. I'll get cancer. It's never true. Is that okay? In fact, the light, when you step out of the room, the sun rays that hits you is more harmful than the radio waves. Because it has higher energy than the radio waves. When you look at the electromagnetic spectrum, the least one is radio waves. You can sleep. That is why you always have fun with us. Nothing will happen to you. Is that okay? So radio waves is the least one and the least harmful. And the most, radio wave is actually around us every day and every time. Is that okay? Because we need that one to communicate. If you are using a phone, I have AirPods. So I connect the AirPods to the phone through microwaves. It's still radio waves that we are talking about. So the AirPods is in my ears. I am not using, the phone is somewhere not close to me, but I can still listen to music or make a call with my wireless AirPods. Is that okay? It's still radio waves that it has connected to the phone, and it will never kill me. Is that okay? So it is very important. And even apart from that, there has been some medical application of these radio waves. We have something we call the MRI. Is that okay? That is the magnetic resonance imaging, where you go in, they use radio waves to take images of some organs and other things if there's a need. So that is radio waves. Right after radio waves, do you know the next wave that follows? Do you know the next wave that follows? Any idea? Okay, let me go back.
Yeah, microwave.
Microwave. But let me go back. Please, let's put this one in our head. Radio wave, microwave, infrared, visible, ultraviolet, X-rays, gamma rays. This should be in your head. This is in terms of increasing energy. If you are asked of increasing energy, this is how you have to name it. So as it's going, it's increasing. It's start from radio. Don't mix them. Don't bring microwave and bring radio wave later. No, it's wrong. If you are asked a question, please arrange it as such. Please, are you okay? Now, microwave. Microwave too has a lot of applications. And a very common one is even our normal microwave ovens. Is that okay? So, do someone know how the microwave works? The microwave that we use to heat our food, do we know how it works? So the microwave that we have in our house, you see, anytime I come to heat food, it has a chamber like this. And it has, now the new ones that has come, it has a plate kind of here. Then you just put your food on it. Is that okay? Then you close it, then you just on it. Now, what this one is doing is, from one chamber here, it's sending some waves. Is that okay? And there's a blockage of these waves of another material that blocks it here. Now, you know the food that we are heating, it has some water in there. It can be very small, it can be more. But what the microwave is doing is that it's able to vibrate these water molecules. Is that okay? And you know that anytime there's a lot of vibration, heat occurs. Is that okay? So the more it vibrates, the more it hits the food. The more it vibrates, the more it hits the food. But in the initial time where microwave started coming, you could put your food in here and only half of the food is heated, like very, very heat, and half of it is very, very cold, interestingly. So they engineered this one again so that, you know, the microwave in the chamber here, it doesn't rotate, it doesn't circulate inside. It only goes through one part, then it's blocked from one end to another one. So they engineered this one so that the food that you have on a plate like this, it rotates. And I think maybe Madam Patient will confirm for me. If you put a food in the microwave, the food will be rotating.
Yes, it does.
So as it's rotating, it makes a uniform the waves going to all parts of the food. Is that okay? So at the end of the day, you will not get one part heated and another part warm. Cooled. All of it becomes very heated. Is that okay? And this one too is very, very free. No harmful ways, no cancer, no anything. No one should deceive you that, oh, microwave causes cancer. No, it's never true. In fact, the sun we are in causes more harm than the microwave because it has high energy than the microwave. Please, are you okay? Now let's go to the next radiation, infrared. This one too has a lot of applications. And I always say this, I think last year or last 2 years, my lab here, it's an optics lab anyways. Someone got a light, then the person told us to check the wavelength of the light for the person. We have an instrument that does that. But my minute light in the bio, I just switched on this thing and I wasn't seeing any light coming out. So I was very confused. Have I spotted it or it was like this before? So my a senior colleague of mine came and told me that because of the wavelength range, it is in the infrared. And the reason is all the waves that I have mentioned, you can't use your eyes to see it unless a detector measures it. Is that okay? You can't use your eyes to see microwaves. You can't use your eyes to see radio waves. You can't use your eyes to see infrared. So the light was on, but I can't use my eyes to see unless we use a detector. Is that okay? And that is infrared. And you know, when our remote some of our remotes, we press it, that want to communicate through infrared. We have even the body. Right now, after COVID, we had one thermometer where you place it on your forehead, then it will give you the temperature. First, the thermometer, you have to get a body contact. You have to put it in your armpit, then you close your armpit. Then for a minute or two, it will sound ping, then the nurse or any medical practitioner checks it and read your temperature. Now, thermometers are contactless. You just place it on your forehead, then you get your temperature. The reason is every human being emits a form of radiation, that is the infrared radiation. So as you are sitting there or you are standing or anywhere you are, you emit radiation. And the human being's emission of radiation is called infrared radiation. I will teach you something where we can relate the infrared radiation to temperature. And that is what is used in the thermometer guns. Is that okay? So we point it on your forehead. The infrared detector in the thermometer reads your radiation and converts it to the temperature for us, which is a very genius way to measure temperature. You don't necessarily have to come and touch you before we feel your temperature. It means that even if I see you from a distance and I have a powerful, very powerful detector, I should be able to even know your temperature. Is that okay? And that is why the satellite up sky is able to read some hot regions in the world or some other part of the countries. Is that okay? You know that, okay, this region is a very high temperature region, this region is a very low temperature region, and other things because of the emission of radiation. In fact, all matter, one way or the other, emits radiation. Is that okay? But some is more than the other. And that is why you see at night, military people can invade your house in darkness. Is that okay? They don't need light. The only thing that they need is to wear vision goggles, night vision goggles, and that one can see radiations, human being radiation. So if I will see you, but maybe you will not see me because we are in darkness. But because you are emitting radiation in darkness, I'll know that someone is standing there and it's a human being. So the military people don't even need light to come and arrest you or go for missions. They wear their goggles and they are good. They can track you anywhere and come and just find you in darkness. Is that okay? So it is very important. Now, let's move to the visible. So the visible, as its name says, it means something we can use our eyes to see. And with all the radiations, the only radiation that we can use our naked eyes to see is the visible. That is why you can see red as red. That is why you can see green as green. That is why you can see yellow as yellow. Is that okay? Because it's a visible light. Please, are we okay?
Yes, sir.
Very good. Then the next radiation that we go is what?
The ultraviolet.
Ultraviolet. I will explain all these things very soon. Let me go to the ultraviolet. So now you see we are entering high energy small. Ultraviolet is one way or the other. Some parts harmful, some parts not really harmful. We the men, when we go to a barbering shop, after the barber has used the machine to crop your hair, they keep it under a light, small chamber, then they keep it there. And that light is, you can see it's a kind of a blue light. That radiation is the ultraviolet radiation. And the main function, do we know the function of that? Anyone?
I think it can
They said it kills germs.
Bacteria.
Is it bacteria or germs? Okay.
Yeah.
Or virus.
We will say it will serve as an antiseptic or disinfectant.
Okay. So it's a way that we can kill this
Microorganisms,
but please, it's not virus. We cannot kill virus. We are moving to extreme. It's hard for you to kill virus. So to kill these things, and even in hospitals, if they're about to do these heavy surgeries, they keep this instrument under UV. Is that okay? Because even if you are using antiseptics or anything, it kills it, but to sterilize it properly, you need it to keep it under a UV light. Is that okay? And it's the same UV light that we can check if a money is authentic or is a counterfeit. Is that okay? And it has a lot of applications. And we can even get vitamin D under UV light. Is that okay? But not an extreme one. You know, we have vitamin D in our body already, but we need a light to induce it so that we get it. Is that okay? So the vitamin D is in our body. We get a little UV, and we get. That is why sometimes people say early morning sun is good. Is that okay? Because you get a little UV there. It induces your body to release the vitamin D for your system. So it also has its own application and a harmful way if you are get exposed to it a lot, because we are moving to high energy. Now let's look at the next energy. The next energy is what?
X-ray.
Okay. Can you help me some of the applications of this X-ray? Anyone, please?
Number one,
it's able to detect the bones in humans. Oh. It captures the bones. It's true, don't laugh.
It is used for it is used for diagnostic purposes.
Okay, how does that one work?
For instance, the X-ray for lump, maybe when there's a lump in the breast of a human being, sorry, a woman, maybe say is it breast cancer or something like that. We can use the X-ray to detect that or to diagnose that.
Yeah, that means it's able to see through something.
Very good. That is what I want to hear.
Yes.
So
see through something.
So you see, now we are entering high energy. And when you reach high energy like this, it's able to penetrate something and allow something. So use that one to answer the question for me.
so we are saying you should answer what question?
That's the use of X-ray.
Yeah, very good. The X-ray.
Yeah.
It's able to see something. When you go and take X-ray in the hospital, what do you capture?
For bones,
It captures
bones
what
and all
the
those
eye
things.
cannot see, like.
Okay.
Internal things.
Yeah.
Internal things, okay. So now with the internal things, what are some of the internal things that we capture?
Like the bones.
The bones, okay.
The lungs.
Yeah.
Are you sure
The
can
teeth.
to check the lungs?
Where did you know?
The teeth.
The teeth, okay. So why is it able to check the bones and it will not capture the stomach?
Because the stomach doesn't have bones.
Okay, that's right. Okay.
So it captures only bones.
Okay. So what you're saying is right. You know, now we've moved to higher energy, a little higher energy. And as it goes, its penetration power goes high. Is that okay? So now X-ray is one that, you know, if the ray passes through your body, anything that is a little softer, it can pass through. Anything that is less, it will block it. And I'm talking about the density of the material. When you look at bone and the muscles, or they say, you know, muscles is a tissue. The bones and the tissue itself is soft enough for X-ray to pass through. Is that okay? So you go and stand in front of an X-ray machine. It takes an image of, say, your chest. All these all these tissues and organs and other things, the X-ray is able to pass through it very easily, right? But because this bones is very dense, it blocks that X-rays. And in a way of blocking it, we take the image and use it for medical diagnosis purposes. Please, are we understanding?
Yes, sir.
And in fact, it's not only medical ways that we use X-rays. Even if we want to check the integrity of some building, we use X-rays. We want to check for internal, say, structure, misalignment, and other things that we can't use our eyes to see. We send X-rays, exactly. But we will look at X-rays again very well I think in the subsequent slides. What is the next radiation that we will talk about? Hey, Madam Patient.
Gamma rays.
Gamma rays, perfect. Madam Patient.
So is it true that whenever you take an X-ray, it reduces your lifespan? That's what I've heard.
When you take, the more you take X-ray, the more you get. You see, now the energy is high. This time around, it's dangerous to be taking it a lot. In fact, if you are even something is wrong with you, the doctor will not advise that you take X-rays in a repeated manner. Maybe if you take this time, you say wait a little bit, then you take another one. Wait a little bit, then you take another one. You need time. And you know, this radiation is high enough to causes mutation of the cells in your body. It's either it will cause a fast multiplication of the cells or kill the cells. Is that okay? So if you are exposed to these radiations a lot, it's either you are creating a cell, a thing like cancer and other things to your body. Is that okay? In as much as this is very, very important, it has some side effects. Long exposure to them is bad. And you know, before I think last decade or something, they realized that the blacks in Ghana here, when they go to US or another country, they die early in the mining company. And you know, when you are working in a radiation, very active radiation companies like mining companies, they wear a tag. And the tag that they wear is to measure the amount of radiation the body has been exposed to. They have a limit that your body shouldn't expose to it. But you know, because the white, they work with hours. The more you work, the more you get money. The blacks that go and work in that company, they hide their tag so that they'll get the time to work more, because the counter will not read more radiations for the company to tell them to go to the house and go and rest. But in the normal way, if you are in the company, and let's say you read 100 counts, the company will tell you, go and rest in the house so that the radiation will dissipate for say a month or two, then later you come back. But the blacks, so very good. You hide the tag and work extra hours. And mining company too, it pays a lot there. So what they realized is a time came and the blacks in there, in a company like the mining companies in radiation active areas, were dying early. And their death it's not a normal death. So they will die and they will have, say, throat cancer, they'll have lung cancer, some weird ways of sicknesses. And it's true because of the excess exposure to these radiations. Exactly. So it's good. It's harmful. Even these radiations, we use some of them to treat cancer. But if you don't take care, another problem. Is that okay?
It gives cancer and at the same time can cure cancer.
Yeah. So it depends on how we are tuning this thing and how we are applying it. When you do X-ray, then I'll tell you something about soft X-ray and hard X-rays. Is that okay?
Okay. Thank you.
Let's go. Another thing is the gamma rays. That is the last one. Very, very harmful. Very, very, very harmful. Is that okay? And if we want to apply this one, it means the research area should be very strong. They should have a lot of money to be controlling this. Is that okay? Because even after using it, disposing the residue creates another problem. There has been an issue where they disposed the residue of a gamma radiation and it killed the whole town. And it's that bad. It's either it will kill or it will create some weird sickness in that town. Is that okay? So again, they all have their good applications but a very bad application in a way. Is that okay? So I think I'll end the class if you don't mind. The next time we meet, I'll go back and do the X-rays very well. Then the things I didn't elaborate on it, I'll do that before we go to optics. Is that okay? I think we're supposed to end. Oh, question, yes, please ask.
Sir, I hope you know that there is a light or beam that is used as an instrument, like a weapon. What type of rays that at times it can cut metals? What type of rays that?
We can use any of the radiations, but most of the times is as can you see the light?
Yeah, you see it as a flash.
Okay, so as far as you can see, it means it's a visible radiation.
Okay.
Any radiation you can see is a visible radiation. But the thing is, maybe the UCC Center, when they are doing physical optics, I will explore them to this. Is how we intensify the light. Is that okay? In your room, maybe you have a bulb that is about 45 watts or 20 watts. If we have a laser, and the laser is the same 45 watts, it can cut between buildings. Is that okay? Because we have one laser here that is 5 milliwatts. 5 milliwatts is very small. It's not up to even 1 watt. It's able to burn my skin if I don't take care. Is that okay? So it's how we have intensified the light. Laser is intensified, it's coherent, and it's monochromatic. So the intensity is very, very high. Is that okay? And it's directional too. So it's not the normal light as a broad light. So if we intensify it, it means it can cut easily. But any radiation, again, that you can use your eyes to see, it falls under what? Visible light radiation. Have we learned something today?
Sure.
Yes.
Okay. So, God willing, next week then we continue. Let's read our slides, I beg you. Okay.
Thank you.
Thank you. Merry Christmas in advance.
Merry Christmas.
Well, Merry Christmas like this is not nice. Please send us more, okay?
Okay.
But I'm patient to send us some chickens, tie and we'll break them.
Me, I don't celebrate Christmas. So.
All right, my lectures
I'm Jehovah Witness.
Because of small gift. Because of small gift. Madam, please say you don't celebrate Christmas.
I'm Jehovah Witness, please.
It doesn't matter. It's because of give you a dodgy.
I hope everyone is fine.
Yeah, by His grace, so.
I bet the calculation we did. Okay. I don't know if there's another group that if people do discussion, chemistry discussion. I'm not in any other chemistry group. Sorry, physics group rather.
Oh, okay.
Yeah, we don't have physics group that we do discussion. I don't know.
I think it will be good. I think it will be good if you form a group discussion on this block 2.
Definitely,
very. This thing I've been fighting for it long time. I think this guy Jerome created a
for physics. Hello.
Madam Patient, we are choosing you as we are choosing to be in charge of that.
No, I will not create that one.
No, maybe if somebody have created
the men should create it so that we the ladies will join. Don't
what men can do. You boys will say what men can do, women too can do.
No, this
that's a lie. That's a lie.
You see, because it's where you are dodgy, you see.
No, we women we are busy. So you men should take over so that we will join. We are giving you the man, so don't worry.
But there is one, or that one is different.
That one was chemistry. We were having one. That one was chemistry.
The
But we never
you said
had good
Swiss online
physics.
centers. Oh, that one is different.
Oh, okay. Me, I thought that one is general, but I thought we can create our
Okay.
personal one that
Okay.
will be serious in that one.
Charlie, it's not easy.
It's not easy.
So
Last block, I nearly gave up.
Hey, like me, oh.
I nearly gave up. That's
It was
what
my
it was.
friend
I'm a housewife.
just advising me to just move on.
Yeah. So this one there, I think in my set, I'm the only one offering physics, so I need more help.
Okay.
Sir Francis should open the group for us.
Let's go to this thing, the main physics.
Okay.
So that we talk over there.
All right.
Right now, I want to enter kitchen small.
That's good. Myself
Okay, so
too.
I need to wait there. Yeah.
Thank you, sis. Bye bye.